A normal distribution is a smooth, bell-shaped curve that describes how many natural quantities are spread around an average value. It is completely described by two numbers. Mean mu, the center of the curve, like the average height of a class of students. Standard deviation sigma, a measure of how far the data typically deviate from the mean, like the typical difference in height between classmates. Key properties. The curve is symmetric around mu, the left side mirrors the right side. About 68% of observations lie within 1 sigma of mu, 95% within 2 sigma, and 99.7% within 3 sigma, the 68-95-99-7 rule. The total area under the curve equals 1, representing 100% probability. The probability density function PDF is f of x equals 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared divided by 2 sigma squared, where e is the natural exponential constant. This formula tells us the relative likelihood of each possible value x. When we set the mean to 0 and the standard deviation to 1, we get the standard normal distribution. It is the reference bell curve that all other normal curves can be converted to via the z-score. The probability density function becomes phi of z equals 1 divided by the square root of 2 pi times e to the negative z squared over 2. Here z is the standardized variable. The curve still has the classic bell shape, but now the center is at 0 and each unit step on the horizontal axis corresponds to one standard deviation of the original data. Engineers often keep a printed copy of the z-table, or use a calculator that lists the area under this curve from -infinity to any value z. Explanation: the z-score translates any raw measurement x from a normal distribution into the standard normal scale. Z equals x minus mu over sigma. It tells us how many standard deviations the observation is away from the mean. Example: suppose a batch of metal rods has length x normally distributed with mu equals 100 millimeters and sigma equals 2 millimeters. A rod measured at 103 millimeters has z equals 103 minus 100 over 2 equals 3, halves equals 1.5. So the rod is 1.5 standard deviations longer than the average. If another rod measures 97 millimeters, then z equals 97 minus 100 over 2 equals negative 1.5, which is 1.5 standard deviations below the mean. Positive z means above average, negative z means below average. Explanation: to find probabilities, we locate the z value in the z-table. P of z less than or equal to z is the area to the left of z cumulative probability. P of z greater than or equal to z is the area to the right, equal to 1 minus P of z less than or equal to z. Sample 1. What is the probability that a rod from the previous example is less than or equal to 101 millimeters? Convert to z equals 101 minus 100, divided by 2 equals 0.5. Look up 0.5 in the z-table. P of z less than or equal to 0.5 approximately equals 0.6915. Thus about 69.2% of rods are 101 millimeters or shorter. Sample 2, probability of being longer than 104 millimeters. Z equals 104 minus 100, divided by 2 equals 2.0. Table gives P of z less than or equal to 2.0, approximately equals 0.9772. P of z greater than or equal to 2.0 equals 1 minus 0.9772 equals 0.0228. So only about 2.3% of rods exceed 104 millimeters. These steps standardize lookup and apply complement if needed are the core workflow. Two handy tricks simplify many calculations. Complement rule: P of z greater than z equals 1 minus P of z less than or equal to z. It converts a right tail problem into a left tail problem or vice versa, because the z-tables usually give left tail areas. Symmetry rule: the normal curve is symmetric, so P of z less than or equal to minus z equals P of z greater than or equal to z in practice. If you need a left tail area for a negative z, you can read the right tail area for the positive z and use the complement. Example, find P of z less than or equal to minus 1.2. Look up 1.2 yields P of z less than or equal to 1.2 approximately 0.8849. By symmetry, P of z less than or equal to minus 1.2 equals 1 minus 0.8849 equals 0.1151. Or directly use the complement rule with the table entry for minus 1.2 if the table includes negative values. These rules prevent the need for separate tables for negative z values and speed up exam work. Critical values z sub alpha are the z-scores that cut off a chosen tail probability alpha. They are used for confidence intervals and hypothesis testing. Common levels two-sided. 90% confidence, alpha equals 0.1, 5% in each tail, z sub 0.05 approximately 1.645. 95% confidence, alpha equals 0.05, 2.5% each tail, z sub 0.025 approximately 1.960. 99% confidence, alpha equals 0.01, 0.5% each tail, z sub 0.005 approximately 2.576. Look up example. To construct a 95% interval for the mean of a process with known sigma equals 3, you need z sub 0.025 equals 1.96. If the sample mean is 50, the interval is 50 plus or minus 1.96 times 3 divided by the square root of n, where n is the sample size. The number 1.96 is read from the z-table at the cumulative probability 0.975, because 0.975 equals 1 minus 0.025. Imagine an engineering company designs a shaft that must be 20 millimeters in diameter, with a tolerance of plus or minus 0.2 millimeters. The production process yields diameters that follow a normal distribution with mu equals 20.05 millimeters, sigma equals 0.08 millimeters. We want the proportion of shafts that meet the specification. Step by step. 1. Define limits. Lower equals 19.8 millimeters, upper equals 20.2 millimeters. 2. Convert each limit to a z-score. Lower, z sub L equals 19.8 minus 20.05, divided by 0.08 equals minus 0.25, divided by 0.08 equals minus 3.125. Upper, z sub U equals 20.2 minus 20.05, divided by 0.08 equals 0.15, divided by 0.08 equals 1.875. 3. Find cumulative probabilities. P of z less than or equal to minus 3.125 is approximately 0.009. Using symmetry, 1 minus P of z less than or equal to 3.125 is approximately 0.009. P of z less than or equal to 1.875 is approximately 0.9693. 4. Desired proportion equals P of z less than or equal to 1.875 minus P of z less than or equal to minus 3.125, approximately 0.9693 minus 0.0009 equals 0.9684. Thus, about 96.8% of shafts are within tolerance. The steps set limits, standardize, red table, subtract are repeated for any engineering dimension or tolerance problem. Another example, estimating the probability that a stress measurement exceeds a safety limit or determining the required sample size to achieve a target confidence level. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Explanation. Below are typical exam-style items that test understanding of normal probabilities and z-tables. Multiple choice example. A component's weight is n of mu equals 50 grams, sigma equals 5 grams. What is probability of 45 grams less than or equal to x less than or equal to 55 grams? Choice A 0.3413, choice B 0.6826, choice C 0.9545, choice D 0.9973. Solution: convert 45 and 55 to z values -1 and +1. The table gives probability z less than or equal to 1 equals 0.8413, probability z less than or equal to -1 equals 0.1587. The difference is 0.6826. So the answer is choice B. Short answer example. Find the 99% confidence interval for the mean of a process with sigma equals 2, sample size n equals 25, and sample mean x bar equals 100. Solution, critical value z sub 0.005 equals 2.576. Margin equals 2.576 times 2 divided by square root of 25, which is 2.576 times 0.4 equals 1.0304. The interval is 100 plus or minus 1.03, giving 98.97 to 101.03. Conceptual question. Explain why probability z greater than 2 equals probability z less than negative 2, and give the numerical value using the z table. Answer: because the normal curve is symmetric about 0. The right tail beyond positive 2 equals the left tail below negative 2. The table gives probability z less than or equal to 2 equals 0.9772. So probability z greater than 2 equals 1 minus 0.9772 equals 0.0228, which is also probability z less than or equal to negative 2. These sample questions illustrate the typical reasoning path. Standardize, use the table, apply complement or symmetry, and interpret the result in the engineering context.